Look at this drawing. On paper it is perfect. The pressures are balanced, the flows are calculated, the logic is flawless. But the real world doesn't care about your calculations. In the real world, walls streak, sensors lie, and operators, well, operators have bad days. In 1974, a chemical plant in Flexiborough, England, was leveled in seconds, killing 28 people. Why? Not because the chemistry was wrong, but because the temporary modification was made and nobody stopped to ask one simple, terrifying question: what if? Engineering is not just about building things that work, it is about predicting exactly how they will fail. In this comprehensive lecture series, we are going away beyond the basics. We are going to dissect the psychology of the HAZOP team, how to manage the loud voices, and hear the quiet experts. We shall explore the physics of disasters in oil and gas, looking at gas flow scenarios. We shall also look at the processing of pharma, where a delay of 5 minutes can turn a medicine into poison. And we are going to the cutting edge cyber hazard. Because in 2026, a hacker closing the valve is just as dangerous as a pipe tripping. Hi, I'm Dr. Fahad and this is the Hazard and Operability Study, or HAZOP. If you think HAZOP is just a boring safety meeting where we fill out spreadsheet for 3 days, you have been doing it wrong. A true HAZOP is a session structured engineering imagination. It is the only tool we have that forces us to simulate the future. Whether you are a student trying to pass your exam or a lead engineer responsible for a $1 billion asset, this session or this series will change how you look at P&ID. You will never see a line again. You shall see a potential hazard. So hit that subscribe button, grab your drawing, and let's start breaking things theoretically. Welcome to the master class on HAZOP analysis. Let's go to work. To truly master HAZOP, we need a complete mental framework, not just a checklist. That is why I have designed this course as a comprehensive 13-module masterclass. We will start with the philosophy of disaster and move all the way to advanced topics like cyber HAZOP and the future of AI in safety system. Now, because this is a comprehensive masterclass, I have divided this video lecture into different portions. You can check the description of this video to find timestamps for each chapter, allowing you to easily find out the specific topic you want to learn and explore directly. Whether you are here for the basics or advanced application, you can navigate specifically to what you need. To ensure you get the maximum benefit without getting overwhelmed, we are splitting this masterclass into 2 parts. In this video, part 1, we are going to focus exclusively on the fundamentals lecture 1 through lecture 5. Then we will see some comparison between HAZOP, HAZID or FMEA and guidewords, and then we will see limitation of HAZOP analysis. We kick things off with lecture 1, where we strip away the complexity and look at the philosophy of deviation. We will define the design intent really means and explain with a systematic step-by-step inquiry. It is the only way to uncover hidden disaster before they happen. The history of industrial engineering is indelibly marked by the movements where the complex interaction of energy, chemistry, and human error resulted into catastrophic failure. To understand HAZOP, one must first understand that disasters are rarely the results of a single catastrophic breakage. Rather, they are often the accumulation of minor deviation, a valve passing slightly, a sensor drifting, a procedure skipped that align to break the system's defenses. The Hazard and Operability Study was developed by the Imperial Chemical Industry (ICI) in the 1960s, not merely as a checklist but as a structured mechanism for imaginative failure modeling. Unlike deterministic method that ask, will this component fail, HAZOP asks, how might the process will deviate from its intent. This distinction is critical. A checklist verifies compliance, HAZOP searches for the unknown. It is a heuristic qualitative risk assessment tool that relies on the collective brain power of a multidisciplinary team to brainstorm potential futures that the solitary designer may have overlooked. This methodology assumes that the design is fundamentally sound, but acknowledges that the physical reality of operations will inevitably diverge from the paper design. This divergence is defined as a deviation, and it is the core unit of analysis in any HAZOP study. The foundation of HAZOP methodology is the rigorous definition of design intent. Every component in a processing facility, from a massive distillation column to a half-inch drain valve, exists to perform a specific function within a specific envelope of parameters. This intent usually includes quantitative target, for example, transfer of 100 kg per hour of reactant A to 50 degrees centigrade, and qualitative goals, for example, prevent backflow to a utility header. When a HAZOP team analyzes a system, they are essentially stress testing this intent. The facilitator challenges the team to imagine a world where the intent is not met. If the intent is flow, the deviation is no flow. If the intent is pressure, the deviation is more pressure. The structured negation or modification of the design intent prevents the analysis from becoming a disorganized brainstorming session and ensures methodical sweep of all physical possibilities. The standard HAZOP workflow is a cylindrical and iterative. It breaks a complex facility into manageable sections called nodes. A node might be a specific pipeline, a reactor, a vessel, or a logical sequence in a batch process. When a node is selected, the team applies guidewords to process parameters to generate deviations. The power of this workflow lies in its exhaustiveness. By systematically pairing every guideword, no, more, less, reverse, etc. with every relevant parameter, flow, temperature, pressure, reactions, the team forces itself to consider a scenario that intuition might dismiss. For example, while a high pressure is obviously hazard, low temperature might be overlooked, yet in a carbon steel pipeline, low temperature could lead to brittle fracture, a failure mode just as catastrophic as an explosion. In lecture 2, we shift our focus to the human element. A HAZOP is only as good as the people in the room. We will cover the psychology of the team, define the critical roles like why scribe is just as important as the engineer, and learn how to stop cognitive bias from blinding us to real risks. One thing we should remember that a HAZOP cannot be performed by a single individual. No matter how expert the desktop hazard, a study conducted by one engineer in isolation is fundamentally flawed because it creates an echo chamber of confirmation bias. The engineer who designed the system is psychologically predisposed to believe it will work as intended. They cannot easily see the flaws in their own logics. So let's see the myth. One of the most persuasive misconceptions in engineering education is that safety is a product of calculation. In reality, safety is a product of culture and collaborations. The HAZOP is inherently socio-technical exercise. It requires cognitive diversity. The intuition of the field operator must clash with the theoretical knowledge of the process engineer. The rigidity of the control engineer must negotiate with the practical constraint of the maintenance lead. It is the friction between these viewpoints that the most subtle and dangerous hazards are discovered. Now let us look at the characters who are responsible to make HAZOP analysis as unbeatable as possible. Number 1 is the facilitator or the chairman. After him there is the scribe, the secretary, then the process engineer, and the last one, the operations representative. After looking at the different responsibility, let's talk about cognitive bias in safety reviews. HAZOP teams are susceptible to several cognitive biases that can blind them to risks. And number 1, the facilitator or the manager, it is his job to actively disrupt these biases by forcing the team to adhere strictly to guide words and justifying their conclusions with evidence rather than opinion. For example, confirmation bias, the tendency to interrupt information in a way that confirms prior beliefs. For example, we have never had a fire here, so a fire is unlikely. Number 2 is availability heuristic, overestimating risks that are recent or memorable. For example, recent spill while ignoring silent, creeping risk, for example, corrosion. Authority bias, agreeing with the most senior person in the room regardless of the technical merit of their argument. This picture shows the summary of chapter 2. Here we see different roles of people, for example, the facilitator, the operator, the process engineer, and the scribe. What are their roles? The process engineer has a large theoretical knowledge. The operator has a large practical knowledge. The facilitator challenges both of them to provide their feedback, and the scribe convert them into documents. And then the facilitator ensure that there is no bias, all the parameters have been ensured, and the HAZOP analysis studied deeply and thoroughly. Now I'm putting few questions in front of you. Why is it considered a critical failure to conduct a HAZOP without an experienced operation representative? And another question, explain the role of the scribe beyond typing. Why is technical literacy essential for this position? You can write your answers in comment sections. Now let us move toward topic 3 or lecture 3. Lecture 3 is where we get technical and learns the grammar of HAZOP. We will explain how to slice a complex plant into manageable nodes, how to select right parameters, and how to use a famous HAZOP guidewords to systematically stress test your design. The first step in the technical execution of HAZOP is noding. A node is a discrete section of the process that shares a common design intent. If a node is too large, for example, the entire cooling tower, the team will be overwhelmed by the complexity and will inevitably miss small localized hazard. If the node is too small, for example a flange or a valve, the study will take months and the team will lose the big picture perspective. Effective noding usually follows functional boundaries. Now what is a functional boundary? A typical node might be suction line from a storage tank T101 to transfer pump P101. This section has a uniform pressure, hydrostatic head from the tank, and temperature. The next node would be discharge line from pump P101 to reactor R202, where the pressure is significantly higher. Breaking the system at the pump allows the team to analyze the specific hazard of the low pressure suction side cavitation leakage separately from the high pressure discharge side rupture or gasket failure. The ISO IEC 61882 standard provides the lexicon of HAZOP, but understanding the words require understanding the physics that represent. Guide words are the deviators that modify the process parameters. This is the list of guide words, and we have some simple meaning with respect to guide words, and also we have some key example. No means complete stoppage or nothing happens, and its examples are pump trip or line blockage. More means too much or quantity increase, valve stuck open or thermal expansion. Less means not enough quantitative decrease, partial blockage or minor leak. Reverse means wrong direction or backward direction, for example backflow through a failed check valve. Part of means missing ingredients or component, crystals not added to mixtures. So here you can observe all the guide words, their simple meaning and keywords. Now let us look at the deep picture of these guide words. Now I have differentiated these guide words into three classes. Number one is physics, on the basis of their physics, on the basis of chemistry, on the basis of operation. No means a physical barrier is happening there. Part of means there is a chemistry part is taking part, and other than means there is a change in operation or there is a problem in operation. You can study this table thoroughly with all definitions, the underlying implications and examples. While the flow, pressure, temperature and level are the primary parameters, complex systems require a broader scope. So here are different other parameters. For example, reaction can be a parameter, a utility can be a parameter, and a time can be a parameter for a batch system. For example, a reaction can have a high reaction rate or a low reaction rate. It can show a low conversion or high conversion. It can be an exothermic or endothermic. So a reaction they had different parameters that need to be controlled. If we talk about utility, so there are different utility. For example, instrumental air, a power, cooling water, or nitrogen or inert air. Availability of these utilities need a proper guidelines whether they are working properly or not. If we talk about time, for a batch system, it has some intent design parameters. For example, 2 hours will take to complete the reaction. If we are giving it less time, so incomplete reaction and yield loss. and if we are giving it more time, so here we see that overheating and degradation of the product can occur. So here is again our example of these parameters. For example, reaction for chemical reaction parameter, reaction rate, conversion and exothermic are crucial. For utilities, instrument air, cooling water, power and nitrogen must be treated as parameter to analyze the loss of support system. For time, in batch process, time is a parameter. More time, reaction runs too long. Less time, reaction quenched too early are critical deviations. Then in lecture 4, we build the analysis engine. This is the heartbeat of the entire study. We will break down the causality chain, learning how to link a specific cause to a consequence and critically evaluating if your existing safeguards are actually strong enough to stop the accident or not. The causality chain. The core intellectual work of the HAZOP takes place in the analysis of the scenario. A scenario is a narrative chain of events. An initiating cause leads to a deviation which propagates into a consequence unless a safeguard intervenes. This linear logic is the backbone of the study. For example, here we see that a temperature has been changed by an operator manually and unintentionally he changed the intended parameters which caused increase in pressure. So pressure of the vessel increased, and here we observe that the pressure needle is going towards the red section, and as the pressure increased there is a PSV valve which ruptured and saved the equipment. So here we see that an initiating cause leads to a deviation which propagates into a consequence unless a safeguard intervenes and the system becomes a safe close. Identifying credible causes. A major pitfall in HAZOP is the identification of the non-credible or consequence-based cause. So there is a differentiation between credible cause and non-credible causes. Let's talk about first credible causes. It can be mechanical, instrument, human or external. Mechanically, control valve or diaphragm fail close or open, pump impeller shear, strainer blockage. So all of these are mechanical causes. Instrument, transmitter drift, false reading, frozen signal. So all of these are instrumental errors. Human cause, operators enter the wrong set point, valve left manual, bypass left open after maintenance. So all of these are human causes. External causes could be power dip, cooling water, header failure, instrument air pressure loss. So all of these are external problems. What if we talk about non-credible causes? It can be something like pipe leak. Unless there is a specific corrosion mechanism, random pipe failure is usually considered a consequence of overpressure, not a root cause. Unmitigated consequences. If there are some parameters which have been left unnoticed during HAZOP analysis, so what can worst happen? To accurately assess risk, the team must evaluate the consequence assuming all active safeguard fail. This unmitigated risk represents the worst case potential of the system. Let's take an example of cooling water pump failure consequence. There are two examples where a pump coming from cooling water has been failed that is used to cool down the reactor. So in first case, if the reactor fails, the temperature or pressure of the reactor will rise up, high temperature alarm sounds and the operator trips the reactor. In this way, the reactor will shut down safely and it will cause economic loss only. But on the other hand, if a pump fails and reactor runaway conditions happens, so it will cause a rupture, and with the rupture there will be toxic gases cloud release. Potential fatalities can be occurred with this problem. So if we compare the mitigated consequences or safeguard, so the high temperature alarm sounds, the operator trips the reactor, economic loss only. But for unmitigated consequence, the reactor runs away, pressure exceeds vessel rating, vessel ruptures, toxic gas cloud release, potential fatalities. The HAZOP must record the unmitigated consequences to determine if the existing safeguards are strong enough or not. If we only look at the mitigated outcome, we might falsely conclude that a simple alarm is sufficient protection for a fatal hazard. Now let us talk about the hierarchy of safeguards. Actually, these safeguards act as barriers to the progression of the incident. In HAZOP, we prioritize them based on the hierarchy of control. So there are 6 ranks of hierarchy of controls. Number 1 is inherently safe design. The vessel is rated for the maximum possible pressure, full vacuum to 100 bar. No active device is needed. Number 2 is passive device. Mechanical barrier like dike walls, blast walls or restriction orifice. In this way we provide boundary to the problematic area. Number 3 is active hardware. Pressure safety valves, ruptured discs, these are highly reliable but can fail. Number 4, safety instrumentation system SIS, automated trips, interlocks that act without human intervention. Number 5 is active human intervention. Alarms, these are valid only if the operator has sufficient time, typical less than 10 to 15 minutes, and means to response. Administrative, procedures, training, signs, these are the least reliable and should rarely be the primary safeguard for high consequence hazards. The HAZOP worksheet is just a list form of the bow tie. Causes are on the left, consequences are on the right, and safeguards are the barriers we erect to stop the timeline from progressive to disaster. Now look at these stages one by one. Stage 1, deviation high pressure happens, which cause a regulator failure. So this regulator failure can result into a rupture, but if we are providing some prevention barrier, for example maintenance time by time, this problem can be stopped. So for example, high pressure can be a reason because of regulator failure or thermal expansion, which can be stopped by a maintenance or thermal expansion by control loop. Both of these causes can result into some consequences, for example rupture and fire. For rupture we have a stage 5 mitigation barrier, for example PSP applied, or a mitigation barrier, fire sprinklers have been installed with the fire catching area. So in this way we can see that a list of hazard consequences or sequences can be converted into a bow tie diagram. Now there are two questions, you can answer them in comment section, or you can see these questions for your interview or vivas. Why is it necessary to record an unmitigated consequence rather than the expected outcome? Question number 2. Under what conditions is an alarm considered a valid safeguard in HAZOP? So you can reply this question with chapter numbers in comment section. Now let us move towards lecture 5. Lecture 5 takes us from identifying hazard to measuring them. We will bridge the gap between HAZOP and LOPA, layer of protection analysis. This is where you learn how to determine if your risks are acceptable or if you need advanced protection like SIL ratings. Modern HAZOPs rarely stop at identifying hazards. They categorize them using a risk matrix. This matrix usually plots severity, impact on people, environment, asset, reputation against likelihood or frequency. So what we do, we make a matrix severity versus likelihood, and in this matrix we quantify the risk. For example, scenario 1, a pump seal leak. Severity minor, S1 type localized spillover. Likelihood occasional, L3 has happened before. Risk low, medium. Recommendation maintenance procedures can be followed to mitigate this problem. Scenario 2, a gas blow by a 2 storage tank. Severity catastrophic, tank ruptures, multiple fatalities. Likelihood remote, risk highly, recommendation LOPA required. Extra layer can be applied to the system. Now layer of protection analysis, where it helps. When a HAZOP identifies a scenario with a high severity, for example potential fatalities, qualitative opinion is insufficient. This study bridges to LOPA, a semi-quantitative method. What are the handshakes? The HAZOP provides the initiating event, for example cause, and the consequences. LOPA assign numerical frequency, for example once per year or 6 times per year for a control loop failure. Independent protection layer. To be counted in LOPA, a safeguard must be an IPL. It must be specific, independent, dependable and auditable. To learn it properly, you can visit my channel where I have uploaded this lecture, a detailed lecture on LOPA. Example, a control loop that maintains level is not an IPL. For a high level trip, if they share the same level transmitter. This is a common design error caught by LOPA. If the LOPA calculation shows that the existing risk is still higher than the corporate tolerable risk target, the gap must be closed by a safety instrumented functions (SIF). The size of this gap determines the SIL rating. If the small gap exists, SIL1 reliability 90 to 99% is enough. If the large gap is present, then SIL3 reliability 99.9 to 99.99% will be ensured. This integration ensures that the safety systems are designed based on actual calculated risk, not just engineering intuitions. Okay, now let us talk about lecture 6. In lecture 6, we are going to clear up very common confusion. When should you use a HAZOP versus a hazard versus an FMEA? We will compare them side by side, looking at their focus, timing and outputs, so you always know the right tool for the job. For example, if we talk about the focus of HAZOP, it talks about process deviations, flow, pressure, temperature. But if we talk about hazard, it is a general hazard, fire, flood, layout. For FMEA, it is a component failure models, mechanical or electricals. So it talks about the component failure. The timing of HAZOP, detailed design and operation. So when the system is running, we can apply the HAZOP. For early concept and site selection, we will use hazard. For FMEA, equipment design, reliability or initial stage of designing, we use FMEA. For method, we use guidewords or nodes for HAZOP, checklist on areas for hazard, component by component analysis for FMEA. Output of HAZOP is process design changes. For hazard, it is a layout strategy changes. For FMEA, it is a reliability maintenance data. Common guidewords interpretations by equipment. So there are names of equipment, general equipment that are used in nearly all industries. For example, centrifugal pump, no flow, it shows tripping, suction valve closed or strainer plugged, or it can show a more pressure, discharge blockage, deadhead has been created, or reverse rotation. It can also show a high temperature. This also represent a deadhead or bearing failure. For heat exchanger, no flow means tube blockage, falling inlet valve closed. More pressure means tube rupture, high to low pressure side. High temperature means cooling water failure, falling bypass open. For a vessel or tank, no flow means outlet blockade, pump trip. More pressure means vent blocked, gas blow by or fire. Or high temperature means external fire, chemical reaction or heater failure. For control valve, fails closed, air failure, diaphragm tear. More pressure means fails open. If upstream pressure is high, bypass open. High temperature means not applicable directly to valve but to a system. So here we see some equipment name and we applied some guidewords and we have seen their consequences that can occur with the change in variation of the guidewords. Finally, we wrap up part 1 with lecture 7 limitation. HAZOP is a powerful but it is not a crystal ball. We need to be honest about its blind spots like human fatigue and external threats, because relying on it blindly can lead to a false sense of security. Further, HAZOP is an indispensable tool for identifying process hazard, but it is not a completely risk assessment strategy on its own. It is best viewed as a powerful hazard identification filter that needs to be supplemented with other tools like quantitative analysis and component level studies to build a complete safety picture. Okay, this is the end of part 1. In next part we will study some case studies and some advanced studies in HAZOP analysis. Okay, see you in next video. Till then, take care.